Lesson 2.6, continuity when we have trig functions and limits for trig functions. The first thing we're going to talk about is continuity. You're finding the values of x, if any, at which we're not continuous. I think about my parent function cosine of x, which is really just that wave of a graph. The -2 is causing a shift to the right. It does not break apart the graph in any way. So this graph has no discontinuities. My sine function normally is a wave, but the input here is now a fraction. What makes something not continuous is when you focus on the denominator equaling 0, that's going to be where you're having discontinuities. So I solve, and the value for where this function is not continuous is when it's at an input of 2 pi. Tangent in the denominator, people may or may not remember when tangent is 0. So if we do some work with reciprocal trig functions, we can think of it as cotangent. Definition of cotangent is cosine over sine. Now I can look at, well, when is sine of x going to 0? That'll be where we have a discontinuity. And memory recall, my picture, y values being 0 are here and here. So we're talking about multiples of pi. So you can either say 0 plus pi n, or you could just say x equals pi n for short. The next denominator equaling 0, to find those discontinuities, move over that root 3, divide by the -2, and I have something that's very familiar, root 3 over 2. We did that in the pre-calc review. And when is that cosine equal to root 3 over 2? Well, it's positive, so I'm dealing with quadrant 1, quadrant 4. Cosine is adjacent over hypotenuse, so I'm looking for the angle right next to the root 3. Its partner is that 30. My first solution, x equals, I need a 30 for a reference, so that takes pi divided by 6 to get 30, plus every rotation back to that spot. Quadrant 4, 3 30s, 6 30s, 9 30s, 12 30s. 1 shy would be 11 pi over 6 plus every rotation back to quadrant 4. 9 plus 2 sine x is equal to 0. I get 2 sine x equaling -9. Sine of x is equal to -9/2 or -4.5. A sine curve normally fluctuates between a 1 and a -1. It's never reaching that value, so we don't have any discontinuities on this graph. 1 plus cosine of x is equal to 0. I'm looking for when cosine of x is equal to a -1. On the graph, cosine is the x value. Being a -1 lands here at -1, 0. So I'm going to say x is equal to pi plus every rotation back to pi. In dealing with continuity, we need to talk about functions that are more complex and their continuity. Well, what we can do to determine the continuity of something that's more complex is we look at it as simpler functions that are known to be continuous. How do I do that? I use function composition. Recall from pre-calc, f of g of x means that you have a function g being put into function f. When I look at this problem to figure out who is the f and who is the g, I would ask myself what is done first to the x, because that's considered inside. The x is being cubed, So my inside function is the x to the third. After I know the value of x to the third, I would then take the sine of it. So that sine of x is the outside function, which is f of x. And if you go back to pre-calc and find the composition of f of g of x, you would do that by taking this x cubed, which is g, replacing it in that spot, and putting into function f, which means I would input the x with an x to the third, and that would go right in here, leaving me with this. You do not have to do it as f of g of x. You can just simply go for identifying who is the inside function, what's being done first, and then what's outside. So in this case, cosine of x is done first. After I know the cosine of x, then I would take its absolute value. So the second function is the absolute value function, so I'm just going to write it as the absolute value of x. So whichever way you would like to do it, you can either identify f of g of x and kind of put names to them, or just go right for identifying the known continuous functions. Little problem here. The next composition is cosine of, and we have a polynomial. Well, we know any polynomial is continuous. So I'm going to say what is done first is the polynomial. That's a known continuous function. After I know the value for the polynomial, I would then take its cosine. So the cosine of x is the next known continuous function. My composition here, I start inside. Cosine of x is the inside function. Once I know its value, I plug it into another known continuous function, which is, again, the cosine. So really, this one is just cosine being put into itself. 12 is a little bit tricky because you have trig functions in multiple spots and powers. The easiest way to think of this one is to think of it as you have a sine of x being raised to the fourth. We rewrote them like that in pre-calcs. 5 sine of x squared minus 2. Then I can easily identify the input, or what's done first is finding the sine value. So sine of x is the known continuous function that's being put in to what looks like what's left is a polynomial function. So we have x to the fourth plus 5x squared minus 2. The last one, this one you could actually write it as, instead of 2, I would actually do 3. If I work my way from the inside to the out, the innermost part of this is linear. So 3x plus 4 is a known continuous function. What is that being put into? It's being put into a cosine function, which is known to be continuous, so cosine of x. And lastly, the last thing you're doing is square rooting, so the square root function is a known continuous function. Back to limits, but now we're going to do it with trig. My first one is I'm evaluating 6 over infinity. That's from the last test. That's my rational function, end behavior. If I go to the ends of that rational function, this piece, 6 over x, is going to 0. So I'm going to say sine of 0 is what I'm focusing on. And the sine at 0, here I am at 0, ordered pair is 1, 0. And the sine of 0 is the y value, so the answer is 0. This one, I'm going to do a little algebraic work here first. I'm going to take the fraction. My end behavior techniques are take what matters for degree. The pi x is the only thing in the numerator, so I'm keeping pi x. In the denominator, 5 is not significant as we go to infinity. Negative 6x is. What happens with this, the degree is matching, those cancel out. I'm really just evaluating the cosine of negative pi over 6, which we were practicing. That means I'm going to go up here. I have a 30-degree angle being generated going down. Right next to the 30 is my root 3. Hypotenuse is 2. So the cosine is root 3 over 2. Same thing, I see a fraction. I'm looking for the end behavior. I'm going to say the limit as x approaches infinity of pi x matters and negative 4x matters at the ends of the graph. 1 is insignificant. That becomes, oops, I forgot to squeak in my sine right there. That becomes the sine of negative pi over 4. My picture, 45 degrees dropping down, negative 1, 1, root 2. Sine is opposite over hypotenuse, negative 1 over root 2. I would pause the video and try the last one and then restart it. The limit as x approaches infinity, cosine pi x over negative x. Those are the terms that matter. When I reduce, I'm looking at evaluating the cosine at negative pi. Negative goes this way. To pi, I land here. Negative 1, 0. Cosine is the x value. This goes to negative 1. My last section. We have limits that we want to commit to memory, but what's going on visually, so you can remember this connection, is I'm taking a sine curve near 0 and then a linear function near 0. I want you to envision focusing in on both of these graphs, getting so infinitely small close to 0. What will happen is that this is going to look like a linear function. This is like a linear function. And if you zoom in enough on your graphing calculator and you had both of them on the screen at the same time, you could do that. Put sine of x into y1 and y equals x into y2. Zoom in on those. As you zoom in and you box it out, you're going to notice that they start to look the same. Because they look the same, I'm dividing same values. That means this ratio goes to 1. Well, if they look the same, its reciprocal would also be 1. If I do any kind of a horizontal stretch or shrink, whatever I do to the sine curve, I'm also doing to the linear function. So you could experiment with that on your graphing calculator. And what will happen is that they're still going to be matching their heights. So no matter what I do for a horizontal stretch or shrink, as long as I do it to both, the ratio is going to go to 1. Now knowing that fact will help us prove some limits. So for these, I'm going to look for, they're kind of like calculus proofs, like you did geometry proofs. These are calculus proofs. Some of you will be getting pretty savvy and be able to figure out the answers, and that's great, but I need the supporting work to justify the answers. How we do it. We take sine of 5x, and I know from up above that if it matches, the linear function matches what I'm taking the sine of, then that ratio goes to 1. So I'm going to do a little splitting apart of my fraction. The 5 is already here, but I don't have an x. So I'm going to put in an x, and I'm noting that I just put in something to a fraction. If you put in something to a fraction, you have to compensate. So what goes into the denominator goes into the numerator, because same things being divided is really a 1, and I'm multiplying by a fancy 1. Well, what do I have left? I've used the sine of 5x, I've used the 5, I have the sine of 8x. That is in the denominator. It'll stay in the denominator. Well, in order for it to become a 1, I need to have a matching amount as a linear function. Well, that did not exist in the original. I put that in. So I'm boxing it out to say, ooh, I put that in. And then I look at the two things that I put in. Well, x divided by x is really a fancy 1, so I'm good there. I have an extra factor of 8. To balance it off, I'm going to put an 8 in the denominator and then a 1 up here because I don't have anything left to compensate for. This becomes the ratio here, because all of this is a group. The ratio of the first one is a 1, the second is a 1, and the third is a 1/8. The answer to this limit is 1/8. I'm going to approach 0 again, and I want to make sure that I match. Do not square. That would be a bad move, because if I think about it, if I take a third and I square it, I get 1/9. Are they equivalent? They are not equivalent. Squaring is not a good option. Splitting and multiplying are your usual go-to methods. I am going to multiply by the square root of x because I'm trying to get a target of 4x in the denominator. So my new expression is going to be the limit as x approaches 0 of, I'm going to keep my sign of 4x, and then the whole purpose was to create a matching 4x, so we're going to multiply those all together. We get 4x. I do, however, have this root x left, so that root x over 1 is kind of like the leftover pieces. Then the first one goes to a 1. The next one I have to evaluate. I'm evaluating it at 0. So I'm going to say I'm evaluating it at 0. Well, the square root of 0 is 0 times the 1 gives me back a 0. Little trig review. 1 minus cosine squared is hopefully looking familiar to you from last year. That is sine squared of x over the 2x squared. Again, it's a proof, and I have to split them apart into known limits. Well, what do we know? If I take the sine of an angle and I divide it by its angle, it goes to a 1. So I'm going to split apart my squared terms as individual terms to say that each of these ratios is going to a 1. I go back to the original fraction, I have a 1/2 left. This becomes a 1, 1, 1/2. The answer for this limit is a 1/2. Tangent is not a known limit. Sines are known limits. So I'm going to do a rewrite and say tangent is really sine of 9x divided by cosine of 9x divided by the 2x. It's a complex fraction. I want to rewrite it so that it is not complex. Dividing by 2x is like multiplying by its reciprocal. So the sine of 9x stays in the numerator. The cosine of 9x is in the denominator. And now instead of dividing by 2x, I'm going to multiply by 1 over 2x. Then I start the splitting of the proof of my limit. Sine of 9x is first. Ideally, to make it go to a 1, I would put it over 9x. Well, this is a 2x, so I'm going to just leave that for later and say I'm putting in a 9x. Times, in the denominator we have a cosine of 9x. This one's a little sneaky. Cosine of 9x is different from sine. When you're evaluating at 0, the cosine of a 0 is 1. Because the cosine of 0 is a 1, then I can evaluate this because I don't have a 0 in the denominator. So because of that, when you see cosines, those are not going to be made into a fraction where you match the inside because that goes to a 1. Times, I have this 2x left, And then I put in the 9x in the denominator, so to balance it, I'm going to put a 9x in the numerator, and now I can see I've balanced things out. Sine of 9x over 9x goes to a 1. We talked about this. Cosine of 0 is a 1. 1 over 1 is 1. The last ratio reduces to 9/2. My answer for this limit is 9/2. Again, a tangent, so I'm going to rewrite it. So the limit as x goes to 0, sine 4x over cosine 4x, and then dividing by sine of 5x is multiplying by its reciprocal. Splitting apart to show the ratios that go to 1. Start with the sine of 4x. Ideally, to make it go to 1, I need the matching linear graph. I put that in. I'm going to make a note to myself. I just put that in. Times, in the denominator, I have cosine of 4x, and just like in the last problem, at 0, cosine is a 1. So that is a safe fraction as is. The last part is the sine of 5x. And to make it go to a 1, I need the linear 5x. I put that in. I'm going to note it. Lastly, I'm balancing everything off. I put in a 5x in the numerator. I can put a 5x in the denominator. I put a 4x in the denominator. I can put a 4x in the numerator. This is one way. You can also have just put the 4 and the 5 because the x balances with the x. Either one is okay. I go, first ratio is a 1 ratio. That's a 1. That's a 1. And this last piece reduces to 4/5. So we have an answer of 4/5 for that limit. 1 minus cosine. We know cosine is a 1. 1 minus 1 is a 0. You're dividing it by 0. So this scenario is a 0 over 0 like we did in the last test. That means, again, if you have zeros over zeros, that's what this is, then I have to rewrite it so that I can make the special ratio of 1. The only way to get 1 minus cosine to become sine in any way, shape, or form is to think about our identities and say, what do I have to multiply by so I can get it to become a sine? The conjugate, I hope everybody was thinking, the conjugate would get me the identity that I need to convert it to sines. I'm going to have the limit as x goes to 0 of multiplying the conjugates together, 1 minus cosine squared, over, and I'm going to keep these in factored form because this is all about splitting and making ones, so you need it in factored form to split it. 1 minus cosine squared is a trig identity. That's your sine squared. Keeping the denominator in, again, that factored form. Now I'm ready to split and make the ones. I have sine squared, so that means I'm going to split them into two fractions. Well, if there's sine x and sine x, then I need an x here, which I have an x, but I don't have another one. So I'm going to put in this x and say, ooh, I just put that in. I didn't have it. Times, and then I have the 5 in the denominator. I don't have any extra constants, so I'm going to throw in a 1. Times, what do I have left? I have the 1 plus cosine of x. At 0, cosine of a 0 is a 1. That means this denominator is going to a 2. I am safe with this one as is. Last thing I need is to compensate for what I put in. I put in this extra x. I have to balance it with an x here in a numerator. Everything is now accounted for. I'm ready to evaluate. We have a 1, 1, 1/5, 1 over cosine of 0 is 1, plus 1 is 2. And then at the very end, you have an x. If I evaluate that x, that's going to 0. Wipes out everything. Final answer is 0. This one is more of like a challenge problem. If anybody wants to have a little fun with some identities from last year and a good mathematical workout, and I would check your work if you were interested in doing it.